Great. So good afternoon, everyone. So my name is Francesco Petruccione. You don't see me, but most of you have probably seen before. And we'll try to fix up our webcam issue before the end of the talk. Yeah. So today is really a pleasure to introduce Dr. Partha Nandi. Yeah. Partha did his PhD in India at the Bose National Centre for Basic Sciences. And since a couple of years, he's a postdoctoral fellow at the University of Stellenbosch in the physics department. Yeah? And today he will share with us some of his knowledge and expertise in quantum aspects of gravitational waves. Yeah, and Partha, we are really very grateful that you made the effort to prepare these lectures for us. And I can see that you have already shared the screen, so you're most and welcome to start. Maybe just one reminder to the participants: we set up this webinar as a Zoom seminar, yeah, so that we can give it a more interactive kind of character. But please be considerate in just unmuting yourself.
No problem. No. I understand. I understand.
Maybe allow maybe Partha will ask you to ask questions at some stage.
Sure,
but
sure.
At the end of the talk, there will be plenty of time for discussion. Yeah.
Sure.
Partha, please, it's your show. You're welcome to start.
Thank you, Professor, for your kind introduction. Can I stop my video? For this time being, I just.
Yeah.
Okay.
Please.
Okay, so thank you, everyone, and let me start my recent lectures on the exploring quantum aspect of gravitational waves. As I can see, most of the audience is belonging from my fellow students, so my approach in this talk will be pedagogical, and which will be which may be boring for the expert, but it will be helpful for the beginners. Okay, so this is the plan of my lectures, and today I just going to discuss our first lecture, which is based on the topic on geometricalization of classical mechanics. And in this lecture, I will show you how classical dynamics governed by Newton's law of motion can be visualized as a geometry of some space. By the way, can you hear me properly? Are you hearing me properly? Hello, can you hear me? Am I audible?
Yes, I can hear you.
Oh, fine. Okay, so and the second lecture, I will discuss a brief overview of the linearized gravitational waves and their interaction with non-relativistic particles. And the third lecture, I will discuss the quantum mechanics of this interacting system. That means the interaction between a quantum particle with the classical gravitational wave. And I will show you what is the implication and what is the motivation behind this combination between this quantum system and classical gravitational waves. And then finally, the most interesting discussion will be based on the detections or the fingerprints of quantum nature of gravitational waves in a quantum detector, and which will be a very important step toward the quantization of gravity in a linearized level. Okay, and finally, I will offer some useful observations and conclusion. So the basic motivation behind this mini school based on this topic is basically, as you or most of them, or you know that in 2015, the detection of gravitational waves is the most successful prediction of general theory of relativity, Einstein general theory of relativity. And it all known that the range of these gravitational waves lies between this frequency range, and which is the latest detection of this gravitational wave and reported in this literature. And the main source of these gravitational waves is basically, it is just for the general audience, the notion of gravitational wave or the origin of gravitational waves is basically due to the black holes mergers or neutron stars merger and give some, and it will release as a, in terms of the gravitational wave. And this process was observed by LIGO and Virgo collaborations in 2015 first. Now, the point is that so far we know that the detection of gravitational wave is a basic classical process, and it is based on the interference patterns of two arms of LIGO detectors. Now, so LIGO's observatory is based on the interferometer experiment to detect this gravitational wave, which is basically a classical setup. Now, the point is that when the gravitational waves passes through the LIGO detector, now the LIGO detector, you know that LIGO detector is based on two perpendicular arms. And this perpendicular arm's length is order of kilometers. But when the gravitational wave passes through these detector, LIGO detectors, which based on two perpendicular arm, due to these gravitational waves, this arm length of this detector is just deformed of the order of 10 to the power minus 18 meter. And this deformation or this distortion of the arm length due to the gravitational wave, when the gravitational wave passes through this setup, this very, very tiny length scale, and which is basically just below to the atomic length scale. And in that length scale, we can't avoid the manifestation of Heisenberg uncertainty principle when you detect the gravitational waves. So this indicates that we should somehow incorporate the notion of quantum mechanics at the level of the detection of process of gravitational waves through the LIGO detector. And this detection indicates this argument or this length scale clearly indicate that the interaction between gravitational waves and the matter should be treated quantum mechanically. And this motivated us to study a new window which is based on to study the detection of quantum nature of gravitational wave, and which was first proposed by Frank Wilczek in 2021. So I will discuss with you our investigation of gravitational quantumness of gravitational waves, how emerge naturally at the level of detection process, and I will show you the most pedagogical way. So first, before going to this original discussion of the gravitational wave setup and the quantum nature, let me discuss with you some prerequisite of this series of lectures. The first lecture I would like to discuss the geometrization of classical mechanics. So as you are already familiar with the dynamics of the particle, when we discuss at the level of classical mechanics, the Newton's law of motion is the most fundamental law of motion, and which basically the backbone of the dynamics of classical system. And this equation is basically indicate that the acceleration of the particle, which is the first term of this equation, is depends on the nature of force acting on the system. But so far we have considered the notion of coordinate in space is just a flat Euclidean space, wherein the distance between 2 points in this space measured by these following structures. And this structure involves this notation. This notation is commonly known as Kronecker delta. And this Kronecker delta is occasionally known as the metric of this space, which define the notion of distance between 2 points. And AB is just degrees of configuration, degrees of freedom, which For general purpose, we just consider for n degrees of freedom or n coordinate components. In practical purpose, it should be 3. We run from 1 to 3. Now, it is a dynamical equation for a single particle system whose coordinate is run from following index 1 to n. And U is just a potential energy. Now, the point is that this equation, when we solve this equation, we get some solution of x, which is the coordinate component, in terms of function of time. Time is just a parameter, evolution parameter of the system, which describe the dynamical nature of the system. So the solution of this equation gives us the classical path, which is known as trajectory. Now, the point is these classical trajectories, when you solve from this Newton's law of motion, it describes the situation where we incorporate the notion of force, because this gradient of the potential is just define the notion of source. And this notion of force or potential incorporate at the level of flat Euclidean space. We never incorporate or never try to understand what is the underlying geometry of this space. We just try to understand what is the dynamical nature or behavior of the system which arises from this classical path. Now, the classical path can be figured out in a different and sophisticated way, because in the Newton's law of motion, it can be noted that it only gives rise to the change of the potential energy. But you can ask the question, you can ask the following question: how to measure the change of the kinetic energy and potential energy of the system if the classical path is deviated, or if we choose some other trajectory apart from the classical. So, and another motivation is that suppose in a particular system, you know the effect of force, but you don't know the actual expression of the force. So in that case, you need to define the classical trajectory in another sophisticated way, and this approach is known as Lagrangian picture. Lagrangian is just a machinery which indicate that you can define some object which is known as action functional. Functional means it is a mapping from a function to a number. Function is a map which is mapped from number to number. But functional is a map from function to number. You can give me a function, I will give you some number. So this is the definition of the functional. And this functional is a functional of the path. So therefore, it is a sensitive to the path. So this object called action is a sensitive to the path followed by the particle. Now, the point is that this can be expressed in terms of the integral of some other object, which is known as the Lagrangian of the system, which incorporate the notion of kinetic energy and potential, which is our interest, because we want to know how kinetic energy, potential energy changes as a particle moves along its trajectory. Now, if we want to understand when the particle choose the particular classical path or classical trajectory apart from the other trajectory or other path, then the answer of this question is just we need to extremize of this functional to select the classical path. Now, this notion of selection of classical path from the action functional is known as the principle of least action. So we can extremize this action and set to be 0, and these give rise to some equation. And this equation give rise to the solution of this equation give rise to the classical trajectory. So this is an alternative and more sophisticated way to extract the classical path or trajectory from the fundamental object, which is called action functional, which also give rise to some other information about the kinetic energy and potential energy, how they change when the particle moves along the trajectory. Now, let me do some step, because when you change the action functional with respect to arbitrary variation of along the trajectory or path, you will get this kind of structure. Now, how will you arrive this structure? Let me do some steps. I hope my screen is visible. See.
Yeah, it's all okay. Thank you.
Okay. Now, we have already mentioned that this S is a functional or integral of Lagrangian, or just which is in my notation, it's just a function of x. Xa dot and parameterized by team. For the timing, we consider some time independent conservative system. But now when you study the variation of the functional with respect to a arbitrary variation, this variation means that you have some time axis and coordinates and some endpoint. Now you can change your path with some arbitrary ways, but the endpoint should be fixed. Now you try to understand under which path this action functional will give rise to the extremum value, and this path known to be as classical trajectory. In order to select this path among some other non-classical or other paths or trajectory, we just consider variation, and we know that this delta L is just give rise to, since the L is a function of coordinate and the overhead dot is just a velocity, then it is just a standard change. This is the point. Now you can also rewrite this term as this part, and also adjust, because you can rewrite this term with some compensating term, which is just basically a total derivative with respect to time. It's some integration of initial and final time. Now you can, the point is that this term, this additional term based on this variation, but we claim that the variation at the end point should be 0. So therefore this term, since it is an exact derivative differential, upon integration, if you substitute the limits of both upper and lower, you will get 0. So now you can immediately observe that the variation of the action in terms of the arbitrary path variation, you will pick up some object inside of the square bracket. So this is the most important object. Now you can rewrite this object just adjusting this minus sign in front of the square bracket. Now the point is that under variation, we'll get this kind of expression. So this is the expression, and I'll already discuss how to derive this expression under the variation. Now, if we claim the variation is just a stationary, the variation of the action is stationary with respect to this arbitrary variation, then this integrand, including the square bracket term, must be 0. And this will give rise to the notion of Euler-Lagrange equation of motion. Now, the point is that this Euler-Lagrange equation of motion should be consistent with the equation of motion obtained from the Newton's second law of motion. Now, if we compare these two equations of motion, you will get the solution of this differential equation, and this solution will be known as classical trajectory, which is a function of time. Now, the point is that when you compare the Euler-Lagrange equation with the original Newton's law or Newton's equation of motion, including this gradient of the potential or force term, you can immediately recognize the explicit form of this Lagrangian up to some additive constant can be identified with this equation. So now this is the important point, because this expression of this Lagrangian completely free from the concept of force law, because this equation, this Newton's law of motion incorporate the force, but these Lagrangians now involve the potential, and the first term can be recognized as a kinetic energy in the flat Euclidean space. Now one can ask the question how one can obtain just equation. Now this point is that here my approach is a reversal. Most of the textbook provide the Lagrangian, then try to understand what is the expression of equation of motion. But here I just want to show you that if you have the equation of motion, which is in particular case I recognize this is a fundamental which describe the dynamics of the system, and if we compare with the original Newton's law of motion, then you immediately arrive at this structure. This structure is a very common structure, and in order to discuss how to obtain this structure, let us do some quick calculation. Actually, we have already discussed that variation of the action is basically based on del t del L del x a dot means time derivative with, of this coordinate del L del x a times the variation, infinite small variation, which must be 0 if it follow the classical trajectory. Now you can plug in the expression for Newton's law of motions instead of this classical. Now you can rewrite this expression as m upon 2 xa double dot, sorry, not two factor, just the acceleration term plus del u del xa times del xa. For the time being, just consider this variation, and so you can just consider the, instead of this Euler-Lagrange equation, you just replace Euler-Lagrange equation by comparing with the original Newton's equation of motion. Now the important trick is we can rewrite this equation in this following way. Now you can also rewrite this expression as, just focus on this first term. Now it can be written as m minus xa dot delta xa dot plus del u del xa delta xa plus d dt of mxa dot delta xa. So you can adjust this first term by splitting two different term, which is just compensating term. Now you can immediately observe this is a total derivative, so you can ignore within the integral, and you can rewrite this as, you can take the minus sign as a common factor, and you can immediately recognize this first term can be written as m by 2 xa dot square minus u. Now you can immediately observe this xa dot square minus u is nothing but your Lagrangian, because the fundamental definition was delta S is just integral dt delta L. So using equation of motion, just using equation of motion, you can immediately figure out what is the explicit form of Lagrangian. This is just a reverse engineering. Any question? Oh, fine. I hope all of you can hear me. Now, so this is the way to extract the form of Lagrangian, which is already given in this equation. So the point is that so far we have already mentioned then how to derive the Lagrangian and from the equation of motion. Now, the important remark. Still, we incorporate the potential. When you incorporate the potential, now ask the question, if we remove the potential, what would be the trajectory? For the free motion means without any potential, without any force, the trajectory is just a straight line. Without any force, particle move with uniform velocity, it's just a straight line. So which is nothing but the shortest distance between 2 points in flat Euclidean space. But for potential motion, if we incorporate the potential term at the level of equation of motion or at the level of Lagrangian, you can immediately observe the trajectory is no longer a straight line. You will arrive at a curved trajectory, but in a flat space. This is the interpretation. You can interpret the trajectory as a curved trajectory in the flat space, but you can also interpret in other way. You can interpret it is a shortest distance, because the straight line is the shortest distance in a flat space time. But you can ask what is the shortest distance in the curved space time, which is called the geodesy. So therefore, whether we can interpret this curved trajectory in flat space in terms of in a language of the Newtonian mechanics, can we reinterpret the potential motion in a flat space as a free motion in curved Riemannian space? So the free motion means the concept of potential can be absorbed, or burden of the potential can be absorbed in terms of the curved nature of space. So this is the point. So therefore, there are two standpoints. Whether you can say it is a trajectory, curved trajectory, but space is flat, or you can just say that your space is itself curved and the trajectory just as a geodesic. That means the shortest distance between 2 points in curved space. Now, we just try to investigate this question. Can we reinterpret the potential motion in a flat space as a free motion in curved space, curved Riemannian space? So therefore, there are 2 points. One is the potential motion. When you say the potential motion, space is flat. But we are trying to recognize the potential in a language of curved but free motion. So in order to achieve this standpoint, we will follow some methodological way. Let us first consider a particular solution of the equation of classical trajectory. So particular solution, say pick up some particular coordinate x1, which is supposed to be the function of time. Now, if this function is invertible, then one can rewrite this time parameter or express time parameter in terms of the x1 also. Okay, so this is just basically reparameterization. So reparameterization means the time is a parameter. By the way, another important point I should say that in this formulation, we are trying to realize the curved trajectory in flat space as a free motion in curved spatial surface, not the curved space-time, because non-relativistic theory do not allow us to time and space treated an equal footing. This is the another point I will discuss later, but this is the side remark. So the time should be distinguished or have some special status in this particular scenario. Time just a parameter, which is we should not incorporate at the level of configuration space or degrees of freedom. So the configuration space degrees of freedom just a coordinate. Now, when you rewrite or re-express this time parameter in terms of this x1 coordinate, which is supposed to the invertible function, then the velocity, that means the derivative of coordinate in terms of time, can be rewrite using the standard chain rule of the differential calculus. And this here I have used the notation which is the x comma a, means this is the derivative of coordinate with respect to the first coordinate, which is x1, and double comma a is just a second order derivative with respect to x1. Okay, so this is my notation. So here I have expressed the first order derivative with time in terms of the x comma a, and the second order derivative also expressed in this following fashion. This is a very simple chain rule of the differential calculus. Now the ask the question, what is the effect of this reparametrization of time? Now time is parameterized with respect to some other coordinate x1. So what is the expression of equation of motion with respect to this new parameterization? So it is very easy because we have already discussed this coordinate. Now the point is that since we are select a particular coordinate which is x1, so if we substitute the expression of x1 at the level of equation of motion, it will be give trivially 0. So that is why we will consider only the equation of motion of other coordinates. So if we have n number of coordinates, if we select only a particular coordinate x1, then the other n minus 1 number of coordinate we can rewrite in terms of the derivative with respect to x1, just using the change of variable. So this second order derivative can be expressed in this particular way, and this entire equation of motions, for simplicity, we consider unit mass of the particle. For this n minus 1 number of degrees of freedom can be expressed in this particular fashion. So therefore, you can immediately observe the equation of motion when re-expressed with respect to our reparametrization. Now we can recognize x1 is our new parameter. Suppose x1 is our new parameter. We just eliminate time in terms of x1. So then the equation of motion looks is completely in different form. It's just not a simple looking form. Now, but this exotic form has some important implication. Now, this is the one other observation is that we can also have the conservation principle, which is conserve energy. Since we consider conservative system, so the conserved energy involve the kinetic energy plus potential energy. Now, this kinetic energy also can involve the square of this velocity. Now, velocity is now expressed in terms of this following expression, and if you express this velocity in terms of this new notion of derivative x comma a, you will arrive at this following expression. This is the expression of kinetic energy in terms of this reparametrization. Now the point is that this expression helps us to identify the change of time, since the time is a function of x1. Now you use please note that here we have used the fact of equation of motion or classical trajectory of coordinate x1, and now inverting the time in terms of x1. So now you can ask how time change with respect to x1. The variation of time parameter with respect to x1 is given by this following expression. It is very straightforward calculation. Now see this expression, this equation of motion, this equation 8 also involve x1 dot square. Now x1 dot can be rewrite in this particular way, and using equation 8 and 9 you will arrive at this following structure. Okay, now this expression, this is the expression of equation of motion using the new parameterization. And this expression, you can immediately observe this first term is just analogous to the second order derivative. Now the second order derivative with respect to the coordinate x1. And this index I is run from n minus 1 number of other coordinates. But this second term has some important interpretation, because now we can ask the question. We ask the question, what is the geometrical meaning of this equation, does it carry any geometrical meaning? In order to answer of this question, let us, for the time being, okay, we have this expression in our hand. Now, let us consider some Riemannian space equipped with metric G mu. What is the meaning of G mu? I have already mentioned G mu define the notion of distance between 2 points in the space. If this space is not flat, then the distance defined in this following way. Now, this is the geometrical object. This distance is the geometrical object, and geometrical object defined in terms of this metric G mu. Sorry, not G mu, this GAB. In our case, it's all a spatial index. Euclidean space, we have already, I just want to remind you, in Euclidean space, this was the role of G mu or GAB played by this Kronecker delta AB. So, which is very trivial identity, diagonal object. But here, at this state, we don't know what is the explicit structure of G. We want to figure out what is the explicit structure of G, which would be consistent with the equation of motion arrived from the Newton's law of motion or classical dynamics. Because our intention is to give some geometrical meaning of classical dynamics instead of saying this is a potential motion. So now, we can also define another functional which is known as action of a point particle with unit mass in a curved space or in a Riemann space with metric GAB. So this is the generalization of kinetic energy, because we know that in flat space, what is the definition of kinetic energy? In flat space, we know that the definition of kinetic energy or action is just integral of Kronecker AB XA dot XB dot. This Kronecker AB is just a trivial diagonal object. If A is B, then it is 1. If A not equal to B, then it is 0 completely. But we don't know what is the explicit structure, because we generalize Kronecker AB to a non-trivial GAB, which could be function of coordinate itself. Okay. Now, this is the generalization of kinetic energy, but never we immediately observe that we never incorporate any additional term which is known as potential, because we don't want to see the potential at the level when you interpret this is a free motion, because we want to understand whether we can reinterpret potential motion in flat space as a free motion in curved space. This is the equivalent picture. Now, if we study again the principle of least action expression, and if we study the variation of this action curve in curve space, just using this standard procedure as we have already discussed, please note that in the flat space action we denote by S. This is my flat space action S. But in curve space we use some different notation which is called I. Now, this curved space case, now we can change the arbitrary variation with respect to path, and you can immediately observe the equation of motion, which looks like this following structure. Now, this gamma is known as, in a context of general theory of relativity, is known as Riemann connection. And this Riemann connection or Christoffel connection is defined in terms of this following expression, and in terms of this following metric is G. So this expression already automatically arrive, and you can immediately arrive this expression just studying the variation or principle of least action using this curved expression. Now again we start the same recipe. Again, pick up some particular solution of coordinate in this expression, so which satisfies, so x1 should satisfy this expression. Now, if we pick up the solution of this differential equation xa dot given in equation 12, now it should be function of time. Time is just a parameter, so therefore time is something which parameterize the curve in the curved space. But still we don't know what is the G. G is some unknown object. Our intention is to figure out the explicit form with some consistency condition. Now this again we can invert this T in terms of the coordinate. This is one kind of reparameterization. Reparameterization means you change your parameter, introducing some other variable. Now using this reparameterization, one can also re-express this equation of motion. Sometimes this equation of, for the particular case, since this Lagrangian or this action do not incorporate this potential, so this gives rise to the free motion, and this free motion in a Kerr space known as the geodesic equation. Geodesic equation means the shortest. The geodesic equation means the solution of this equation gives the shortest distance between 2 points in this curved Riemann space. Now this, when you select a particular coordinate, say x1, say for the other n-1 number of variable also can be rewrite using this reparameterization. But here you can immediately observe. Here you can immediately observe the moment you rewrite. See, this expression. This is the geodesic equation for n-1 number of coordinates, but with respect to time. So therefore this dot, overhead dot, indicating that we are taking the derivative with respect to time parameter. But now we are selecting some other parameterization. So new parameterization, when you change this change of a variable, and you can immediately observe this new parameterization or reparameterization will give rise to the expression of this above expression in this particular way. Now you can immediately observe that this notion of gamma is now looks different, and we already mentioned the definition of gamma hat. Gamma hat means we have some different expression, and which is looks like this structure. And we have already mentioned what is the explicit form of this gamma. Now the point is we have this structure, equation 14, which arise from the reparameterization of this curved Riemann space. And we have also obtained the equation of classical dynamics arising from the action principle or Newton's law of motion. Or you can say this is the equation for potential motion, and this is the equation for, this equation 14 is the equation for free motion in curved space. Now, if we say both of them are equivalent or both of them are two different sides of same coin, then you can compare two equations. So we can compare this equation 14 with equation 15. Equation 15 is nothing but previous equation, equation 10, just assigning different equation number. Now you can immediately compare by straightforward comparison of the second term, because this second term also involved, by the way, there are some misleading because this dot is not there. It should be corrected because this is a typo. This should be x comma a, x comma b. Okay, so there is no dot, because you can immediately observe that the previous expression involved the comma. So I just use the same equation. So this should be derivative with respect to x1, not t. So now when you compare, you can immediately extract the definition of gamma hat and also extract the definition of gamma, this original gamma. So by comparison, the straightforward comparison between two equations, because we demand both of them describe the same system. One is the potential motion, other is a free motion, but the burden of potential shifted to the curvature metric. This is our intent. This will be our intention. So therefore, one can immediately arrive at this is the explicit structure of the Riemann connection or Christoffel connection. One can immediately observe this Riemann connection. By comparison, one can define in terms of the potential energy U. Now we have the other conserved quantity in this picture, because we have already observed that When you have free motion, the total energy should be conserved. So therefore, this is the conserved quantity, and this object within this bracket is denoted by V square. V square is a dimensionless quantity, and it will satisfy the on shell, means this xa dot xb dot are nothing but the solution of this equation, this geodesic equation. So therefore, this is called the on shell. On shell means the coordinate derivative or coordinate satisfy the equation of motion or classical trajectory. Now, this definition of this conserved quantity or conserved charge, any this conserved quantity help us to extract the variation or change of the old parameter with respect to new coordinate x1. I mean, this what is the change of t with respect to x1? Because we have already mentioned we reparameterize our t with x1. Okay. Now, with respect to this change of variable, I mean, not change of variable, with respect to this change of time with respect to x1, we can extract the expressive structure of this dt dx1. And we have already noted that in our potential motion, we also extract the change of t with respect to x1. So same recipe apply for this particular scenario. Now the point is that from the potential motion in flat Euclidean space, we also have this expression, and the free motion in curved space, we have this expression. Now, if we again claim both of them are two different sides of same coin, means the potential motion in flat space, curved motion, free motion in curved space. If we say these are two equivalent description of same system, so we can immediately compare, and by straightforward comparison, you can immediately observe this GAB, the trick, is no longer flat Euclidean because it incorporates the notion of potential. So therefore, this is our achievement of our claim. Our previous claim is that how one can reinterpret these dynamics in flat space with potential in terms of curved space, free motion. So therefore, curved space is just extract from the potential energy, because if you remove the potential energy, it is just a trivial Euclidean flat. Euclidean flat means metric is just a trivial Kronecker delta. So this straightforward comparison help us also to make some important comment. So therefore, the point is that one can have whether we now we have the metric in terms of the potential energy. And also we know that the metric satisfy this condition. This condition is very important. This condition is just called the metricity condition. So therefore, Christoffel connection also should be rewritten in terms of this metric. Now, the point is that we have the metric. Now, if we re-express this Christoffel connection in terms of this metric, does it consistent with this expression of the Christoffel connection in terms of potential? So this is the question. So therefore, we already have this expression. We have already the expression of this Christoffel connection. But the question is, does this expression consistent with the definition of Christoffel connection using this metric, using this given metric? Because you know this V is arbitrary, because V is a conserved quantity. It can take any value. Now, if I compare this fundamental definition with our derived expression of Christoffel connection, one can fix up this arbitrary constant V, and we can immediately observe both pictures will be consistent if we demand V is 1. It is a straightforward calculation, but the point is that, I mean, we are not interested in to do how to calculate or how to compare these two expression, because the essential message is if we compare two expression, one is given in terms of potential and one is given in terms of metric is given in terms of this potential, this arbitrary constant V square is fixed by 1. So there are no ambiguity of this V of constant. Now, so therefore we achieve our goal, because the free motion in curved space can be described completely in terms of this curved metric, which has the geometric interpretation. So therefore, this clearly indicates that if we have the potential motion in a flat space, we can also shift the burden of the potential in the metric of the curved space. So therefore, we can modify the metric of flat space by absorbing the potential, and we arrive at a new Riemann space. We're not claiming this is the space time. This is the space, again space, because time is just a parameter here. Now let us come back to our original plan. The plan is that when you incorporating gravity, so this is just a baby version of the gravitation. Gravitation means in the gravity there are no concept of potential. Everything is just in terms of curvature. So now when you discuss the concept of gravity and gravitation, you can it should be a relativistic theory, and the relativistic theory, time and space both treated at an equal footing. So therefore, we introduce some other parameters. Say tau. Tau is just called the affine parameter. I will discuss what is the meaning. Affine parameter means this parameter related to the coordinate time with this particular transformation. So those parameters which is linearly related to the ordinary coordinate time, this is called the affine parameter. So the point is that in this particular way, we can treat time also the part of coordinate, and both time and space make a 4-component object which is be treated as a point in a curved space time. Now we can also re-express our geodesic equation in a most covariant fashion. Just replace all spatial index in the space-time index denoted by mu nu, and the t now replaced by the proper time. This proper time parameterization is defined. So now the point is that I will show you here proper time define the length element or the line element in curved space time, where this curved space time equipped with this metric g mu nu. And again, the same way, one can also define the dynamics of a particle on this curved space-time. That means you can extend this concept. So the point is that we want to geometrize this classical dynamics in a language of curved space. And this exercise also can be extended at the level of this gravitation theory in the relativistic gravitation theory. I will discuss more on the topic in the next lecture, but let us highlight what insight can be drawn from our today's discussion. Today's discussion, we demonstrated that the system configuration space can be endowed with a metric, and the metric incorporate the potential. Now, if we remove the potential, then this metric is just goes to flat metric. So therefore, this clearly indicate if we have the potential in terms of potential, we can also define a curved space or Riemann space. What is Riemann space? Riemann space means which has satisfied some important description and which satisfy the Christoffel connection in terms of metric. Now, the potential motion, the point is that the potential motion in flat space is thus equivalent to free motion in curved space, because when you reinterpret your potential motion in curved space, don't need to invoke any additional potential term, because curvature itself the source of force. This is the standpoint of Einstein. So then the trajectory of the potential motion coincides with the shortest line of the Riemann space. And additionally, for non-relativistic particle dynamics, one can also define the geometric interpretation of the time interval. Because time interval, you can immediately recognize this expression, this expression, this dt dx1. Now dx1, now this coordinate x comma a, x comma b is just a derivative with respect to x1. Now if you multiply both sides by dx1, now you can extract this dt in terms of this object. This object is denoted by gab times dxa dxb. So therefore time interval has some geometrical meaning, or it is an invariant object in the curved space, just like the proper time description in relativistic space, curved space time. For relativistic curved space time, proper time play the role of evolution parameter, and the non-relativistic case, the coordinate time itself will play the role of evolution parameter for the dynamics. And these open up a new question. This formulation, one can carefully observe, our system is a conservative system which incorporates some potential which is only function of x. Now, we can show, we have already shown that the potential itself enough to define the new curve space metric. But can we adapt the same strategy, include the velocity dependent potential term at the level of action? Just like when a charged particle moving in a magnetic field, you know that due to the Lorentz force, the Lagrangian incorporates some velocity dependent potential. Just like I just want to show you that. So if you have the charged particle magnetic field, the Lagrangian looks like m xa dot square plus E by C A xa dot. So therefore A satisfy the curl of A is B. A is the vector potential. So therefore you can immediately observe this can be regarded as a potential term, another potential term, but this is velocity dependent. So the question is arise whether this formulation also consistent for the velocity dependent potential, so that whether we can again extract some curve space incorporating some velocity dependent potential term in the Lagrangian when you define in terms of the flat space geometry. So this opened up a question, and I just request you the students think over it. So I think we can stop here. Thank you.
Yeah, Partha, thank you very much for the excellent and very interesting lecture. And as I said at the beginning, this is set up as a seminar. So if you have questions for Partha, just unmute yourself and ask. Yeah.
Okay. So
Sir, I have a question.
Yes.
Can I ask it?
And please,
Yes, yes.
it would be really nice, maybe if while you ask the question, if you briefly introduce yourself and switch on the video so that we see you.
Okay, sir. Just give me one moment, please.
Pleasure. No, because we want to try to give a human touch to these virtual meetings. Yeah.
Yes.
And it's nice not to speak to avatars. Okay, if it is complicated, it doesn't matter. Yeah, if here we go. Excellent.
Yeah,
Hi.
he looks nice.
Hello, sir.
Yes. What is your question?
My name is Partha Nandi, as you can see in the screen, and I am a master degree student and pursuing my master degree in Calcutta University currently.
Excellent, please. And you're welcome to ask the question. Yeah.
My question will be to the Partha sir, that in this derivation, he on the first step he considered that the time is a parameter in non-relativistic consideration of this system or this derivation, but then he inverted the whole thing and he claimed that the time is a parameter of the position. But as we are in non-relativistic domain, so can we physically say that the time can be inverted into the function of position?
Yes,
I mean,
yes,
is it a physical thing?
It has some meaning only along the trajectory, because the trajectory is a function of time. Now you can ask the question whether time can be rewritten in terms of the function of x. So therefore, it is only possible if this function is invertible, and it is only possible along the trajectory, not the arbitrary path. Okay.
Okay, sir. Okay, thank you.
Excellent. Thank you. Partha, there is a raised hand by Joseph.
Yes.
Kiwi. Joseph, please just unmute yourself and ask the question.
Yes. Good afternoon, colleagues. Yes, thank you for the interesting talk on gravitational waves. Now, you indicated that these waves are generated or they originate mostly from
Black hole merging or
neutron
neutron star
stars,
merging. Yes.
neutron stars rotating around each other, and then in the end, so neutron stars and the black holes. In what other cases do we have generation of gravitational waves?
Yes, sorry, I can't
In
follow
what
your
other
question.
circumstances do we have gravitational waves being generated or
Yes.
being produced?
Yes, I mean, when you have this situation where two black holes merge together, when you have two supermassive black hole or two neutron star is merged together, then there is some vibration or some deformation of the mass distribution in a galaxy. And this mass distribution, this mass is your energy momentum distribution is the source of gravitation. And this deviation or this excitation of this mass distribution due to this merging of black hole or neutron star releases energy or releases waves. These waves is just like electromagnetic, just like a situation. When you have a charged particle and you consider a charged particle is just accelerating. Now the accelerating charged particle emit the radiation, electromagnetic radiation, which is known as light. Okay. So in the similar situation can be extended in the context of the gravitation or galaxy. When these black holes merge together, there are some shock and there's some release in terms of this gravitational waves. Okay. Is it answer for your question?
I assume that Joseph is happy with your answer. Thank you very much. Are there further questions for Partha?
Yes.
Please, just sorry, I don't see any raised hands. Partha, if nobody steps up, I assume that everything is clear for now. Then it is just my pleasant duty to thank you very much for the nice lecture.
Thank you.
And I will sorry, there was a comment in the chat regarding the slides. So if you share them with we can upload them on the NITEX website. So they will be published next to the link to the recording of the lecture. Yeah.
Okay. Sure.
And just a reminder, please come back next week, same times. And if you have friends and colleagues that are interested, please advertise it. They can still catch up by watching the first lecture on YouTube, probably by tomorrow. So it should be uploaded. Yeah. And Partha, I definitely owe you a coffee.
Thank you.
Thank you very much. But we can sort it outside in the real world, not in Zoom.
Yeah.
Excellent.
Okay.
Thank you very much, everyone. Have a